everyone, welcome to this presentation. I'm Saloni Garg, and today we'll discuss a very important and practical question that keeps coming up quite a bit, especially when you're designing a vector search infrastructure. CPUs versus GPUs. When do you need a GPU? When is CPU just good enough? How do you manage the trade-offs between speed and cost? In this presentation, we are going to talk about what vector search is, what does a pipeline normally look like, what is CPU versus GPU architecture in general, and then we'll talk about how the hardware constraints are going to interact with your algorithm choices for your specific model. We'll also talk about the cost models for both CPU and GPU, and then we'll talk a little bit about the optimization techniques for using a hybrid approach. You can actually use some part of your model on CPU and some part on GPU, and then we'll talk about some case studies especially related to RAG-based systems. So let's talk about what is vector search and how is it different from the old lexical search. What happens in vector search is that suppose you have an input document or an input image. Let's say you have an input document that comes into your system. The transformer model that you have will generate an embedding that will be a d-dimensional embedding and store it in the system. So you'll have a corpus of these d-dimensional embeddings. Now, for example, a query comes into your system and it interacts with the corpus of these embeddings that you have. The system will try to minimize the dot product. You can have another kernel instead of dot product as well, but the system will try to, for example, let's say your kernel for now is dot product, then the system will try to minimize the cosine distance between these two. And then the top k results that will be generated will be returned as the most similar or most relevant search results. Now, just to understand it a bit better visually, let's talk about the whole end-to-end vector search pipeline. So we have the data ingestion piece, data indexing, querying, and then post-processing. First of all, let's talk about the ingestion piece. This is the most compute-intensive piece in our whole pipeline. We have raw data, like raw text, image, or audio data, and that gets converted into a vector embedding. This can be done by an LLM or a clip-based model or any transformer model for that matter. The input that this is going to get is raw data, and the output is going to be a vector embedding. Next is the indexing piece. So here we're going to build an ANN index. Basically, a vector-to-vector lookup is what is going to happen in the querying piece. So we're building an ANN index, an index of vectors. Next is the querying part. So given a query vector, you're going to retrieve the top k closest vector. For that, you're going to measure the cosine similarity or any other kernel for that matter on your whole corpus of embeddings. And the output is going to be the top k most relevant, the closest vectors to the query. And the last is the post-processing piece, which is actually a little bit optional, not really, the main thing in scope for this video. This is just, think of it like, any business rule filters or re-ranking using sparse scores or any LLM re-rankers. That is what is going to be included here. Let's take a look at CPU versus GPU and the architectural differences in the two. So first and the most important difference is the core count. For CPU, the core count is going to be 4 to 64 cores on an average, but for GPU, it's going to be in thousands, which makes the whole difference, honestly. So this actually helps the GPU to parallelize the processes better and to have the speed that it has. And next is memory bandwidth and latency, which are going to be low in CPUs and very high in GPUs. Next is parallelism. So for parallelism, it is going to be moderate in CPUs and massive in GPUs, which is possible because of the high number of cores and the architecture of GPU as well. Next, we have the cost, which is again the most important piece. So cost of CPUs is going to be very less, but GPUs are going to be 2 to 5 to 10 times more costlier than the CPU. So yeah, GPUs have thousands of cores for SIMD workloads. But the performance doesn't really depend on more cores. This is not really, the only factor that influences the performance. If the model doesn't, vectorizes well, then we are not going to see a significant increase, even if we are running it on GPUs, on a very costly GPUs. We'll talk about that in, later slides. Now let's talk about the part when CPU actually performs better than GPU or actually performs just fine. So number one is when the dataset has less number of vectors. Let's say that when the dataset has less than 1 million vectors, in that case, the GPU initialization piece and the memory transfer, those can actually outweigh the performance gain, and that is why the CPU ends up performing better. So next one is low latency. If the model that you're running is really latency sensitive, and for example, you need, let's say less than 10 milliseconds of latency end to end, in that case, CPU performs really good and better than GPU because, CPUs actually allow for a tight application logic. So For example, you have user-based filters or metadata constraints or real-time personalization. These kinds of logic branches often perform better on CPU compared to GPUs. Third is hardware utilization, SIMD, quantized indexes. So like modern CPUs these days have they can use SIMD to accelerate distance computations. And we have libraries like FAISS which do exploit the instruction set on modern CPUs for highly optimized top K inner product or L2 scans. When these are combined with the quantized indexes, they give you a very strong balance of speed and memory efficiency. Last is cost sensitive apps. So if cost is one of the major factors in your decision making, then you are going to definitely prefer CPUs or a hybrid approach at the very least. Next is, when is a GPU better? So a GPU is better in a lot of cases, not all the cases, but a lot of cases, definitely. So first one is brute force or batch heavy queries. For example, you're running a brute force flat search, then your GPU is definitely going to be better because it can parallelize better, it can assign more cores to your model. So the inference is going to be much faster compared to a CPU. Another thing is FP16 matrix multiplication. So if you are, this is one of the things in which GPU really shine, matmults. So if your model has a lot of matrix multiplication, FP16 multiplications, or large batch ANN queries, then we are definitely going to consider GPU as well, again because of the way it can parallelize. It can make use of multiple cores at the same time to parallelize. But then you should know how to use CUDA kernels or any other you should know how to write custom kernels to make inference better suited for your particular model on a GPU, to make sure that you're making the best use of the GPU that you're paying for. Next is the benchmarking strategy. So when it comes to using CPU versus GPU for your vector search, you have to use benchmarking. You cannot let this is one of the most important pieces in deciding what your infrastructure strategy is going to be. And while we have a lot of open source data sets like Deep1B, Sift1M, Glove 1.2 million, but still I would recommend that you use a slice of your own real data to make sure that this infrastructure strategy is very well suited for your real data as well, and not just some open source data sets, because these are definitely going to show really good results on GPUs in most cases. But then based on your real data, the model that you have, you would want to still understand how this divide or the hybrid approach is going to work in your case. And these are some of the tools that you can use: FAISS, Scan, BB8. These are some of the open source widely available tools that people use to benchmark the model performance. Next one is the metrics. So these are some of the very commonly used metrics like latency, throughput, recall, cost per hour, and energy consumption that you can base your decision finally on. So one thing is that you would want to test this on multiple index types. So by index types, I mean like flat indexes are going to give you exact recall, but then they are computationally very expensive. IVF, which is another index type, is going to provide you with an approximate results with less accuracy, but it scales better, and the performance is going to be significantly faster on CPU versus GPU. So yeah, you would want to make sure you're using the correct and robust benchmarking strategy based on your model, your data, and your cost and latency and other metrics that matter to you. Next is cost considerations. So GPUs are going to give you a high query per second, which in turn means high dollar amount as well, right? So this there comes up another different sort of dimension that you need to worry about, which is not just the cost in absolute dollars, but cost per query, because GPUs are going to give you most definitely going to give you higher QPS compared to their CPU counterparts. So that means more more queries, more cost per query, and more cost in general. Then GPUs would give you really good throughput. You can see they are 4 to 10 times more expensive per hour than CPUs, and which makes them even more costly since the QPS is high as well. So that reminds me of batching. Batching is super important in the case of GPUs. So if you're not using batching, if you're not using large batch sizes on GPUs, then you're kind of wasting the cost that you're paying for the compute cycles on GPUs. So batching is super important to make your GPU actually economically better suited choice. The next one is spot instances. So spot instances basically mean ephemeral instances, kind of. What they do is that they can actually slash your bill, your cloud bill, in half at least, because when they are not in use, they close out, they get destroyed themselves, and then they spin up when they are needed. So yeah, that is one of the very important considerations that you can make use of. However, if latency is your top choice, then you might not want to go with spot instances because of the cold start problem and a lot of like other factors. Next is cost per query versus SLA trade-off. So again, the same thing. So cost per SLA is something that you need to care about, like how much latency. So how much latency are you able to take, are you able to like tolerate for a lower cost per query? This is the answer that you need to find yourself based on your business conditions, and that will help you answer what sort of hybrid divide is going to be there between CPU and GPU machines. It is actually important to discuss about some CPU optimization techniques. So for whatever reason, if you are running the entire workflow on CPUs, or you are running a hybrid approach, it is important to optimize the CPU using these techniques for your model. So first one is use SIMD and multi-threading. So you would want to use multi-threading, which makes sure that you're using all the cores as much as possible. There are some libraries like FAISS which are actually designed, like they have this strategy to sort of exploit the intrinsic based distance kernels. So yeah, make sure that the model that you're using is you're using it to the fullest. Basically, if it is optimized for multi-threading, then make sure that you are making the best use of that, because in CPU basically we do not have a lot of leeway to play around with inference. We have a very narrow sort of region to play around with. Next is quantization. So by quantization, this is sort of self-explanatory. We can convert our 32-bit floating point embeddings into smaller 8-bit embeddings, which will slash down our memory and also slash down our like anything in memory, like our cache pressure and those things, our memory footprint in general, basically. So it's important that if accuracy is not super important, then we make use of quantization and put less pressure on the memory. Next is memory mapping and NUMA-aware processing. So memory locality is going to matter quite a bit in cases of CPU, as we also talked about the cases in which CPU performs better than GPUs. The reason is because of the locality of the data, and the mapping of the memory is the main reason here. So you would want to use memory mapped indexes to load everything into RAM, which is really good for large models or sharded deployments actually, because you cannot just load every single thing into the memory. So you should use NUMA-aware memory pinning, which is sort of out of scope for this video, but it is an important CPU optimization technique that is good to know about. Next is optimize the index size for IVF or IVF plus PQ. So index tuning is super important again. IVF is fast, but only if your coarse quantizer is well parameterized. It is only useful and fast if if the coarse quantifier is well parameterized. So yeah, you would want to use enough centroids to maximize the candidate set size, but not so many that you increase the lookup overhead. So there is a balance that you need to strike between the number of centroids that you would want to have. Let's also look at some of the GPU optimization techniques, which are really important, because you cannot just have a really good raw hardware and expect your model to work really well. The reason is because you still would want to optimize for your GPU and make sure that you are if you're paying such a high cost, you're making sure you need to make sure that you're making the best use of your hardware, right? So you need to optimize the data flow, and you also need to optimize the whole compute pipeline, sort of end to end. So let's talk about these 4 ways that you can do this. First one is CUDA streams. So CUDA streams or QBLAS is they allow you to basically launch multiple kernels asynchronously, so that you are overlapping the memory transfer with computation to reduce the idle time. You're making sure that both the memory transfer and the computation are happening sort of parallelly, so that you do not have any idle time. Especially, the problem or the good thing with GPUs is that they are able to give you a really high QPS, which means that your model is going to receive a lots of, like, let's say thousands of queries per second. So in this case, these become, like, optimization techniques become especially more useful, because you're looking at thousands of queries per second. So yeah. Next is FP16 embedding search. So FP16, floating point 16 embedding search is sort of like GPUs like A100 and L4. They have native support for half precision, like FP16. So by storing embeddings in FP16 and the running search computation in lower precision, you are making sure that you are reducing the memory by at least 50%, or that's just a ballpark figure, but you are making sure that you are reducing the memory usage like that, and you're doubling the memory bandwidth as a result of that. So yeah, next thing is kernel fusion. So in vector search, top k selection is often the bottleneck for distance metrics. Once you have the distance metrics computed, you would want to run a separate kernel for distance computation and another kernel for partitioning. So instead of running these two kernels, one for distance calculation and one kernel for partitioning, you would want to combine these both into just one kernel. So this approach is actually going to reduce the memory traffic and latency. Next one and last one is N-side profiling. So N-side systems, they are basically a tool that let you sort of visualize kernel launches, memory bottleneck, and any transfer delays if possible. So you can run these sort of like profiling systems and then find out what piece in your whole pipeline is taking the most time. Where is your pipeline stalling basically? Is it waiting on memory for a lot of time, or waiting on compute, or just synchronization? And then this way you have a more deeper view of the problem, and then you can take measures to fix that. So embedding generation is actually a very heavily overlooked piece in this whole performance bottleneck. The reason is because we would think that embedding generation is a very important and must-have piece, so we cannot really remove it, or there are it is more or less standardized, but that is not the case. Let's talk about these three sort of ways. First is embedding models like BERT and CLIP are GPU heavy. These models are incredibly powerful, but they are also GPU heavy. So if you're generating the embedding at query time, then this piece is going to add to your latency budget, right? So the best strategy is to consider splitting inference and search pipelines. So decoupling the inference and search pipelines is going to be really helpful for you. You can separate them, especially if you think your embeddings can be reused. For example, you have one recommender system, one is ads retrieval system, and you have your user embeddings generated, which can be used in both your recommender system and ad generation system, right? So this sort of this is going to help you quite a bit in reducing things that matter in your latency budget, right? Another thing is that you would want to cache the previously seen queries, or just run offline batch embedding jobs so that you can store your vectors in a key value store or a vector database. This way you're not adding this piece to your latency budget. Next is use ONNX or TensorRT to accelerate inference. So another thing is you would want to, especially if you need real-time inference, then you should convert your PyTorch or TensorFlow model into ONNX and then compile it using TensorRT or OpenVINO, and this will give you a 2 to 5x speed up in your inference, basically, with reduced latency and lower memory usage as well. So you might want to consider, this should be like a good fine-tuning step for your whole infrastructure in general, even if you're not really craving for real-time inference. Additionally, there are some tools like VLLM or DeepSpeed, which are specially built to, help you when you're batching multiple queries or streaming across token windows. So yeah, take a look at VLLM and DeepSpeed and see if you are, if you can make use of them, especially if you're batching multiple queries at the same time. Lastly, it's up to you, but you can, if you're considering a CPU or GPU setup, you can have CPU for search, GPU for filters, for actually the query filters, or you can have GPU for embedding generation and CPU for ANN or approximate nearest neighbor search. You would want to orchestrate them using Ray. Ray is a super popular, sort of orchestration system used in ML workflows these days. It is open source, so it is a really good, way to sort of orchestrate your whole ML pipelines using minimal coding. It offers a lot of like modules that you can use, just that have a lot of functionalities pre-baked. And then you would want to align infra to compute hotspots, whatever is the piece in your whole pipeline that is taking up most compute power, most memory. You would want to align infra according to, you would want to have that piece run on GPU, for example. And Insight system, as we talked about in the last slide, is going to be a really good thing that will help you recognize this. Now that we have learned everything, sort of theoretically, let's apply this to a case study example of RAGs. For this example, let's say we have a document retrieval, system for LLMs. So in this case, we have the first piece, which is embedding generation. This is actually the most compute intensive piece in this whole equation. So we are going to use GPUs to perform this. What this does is that we have the raw documents and any transformer based model that is going to generate embeddings based on the raw document. Since this is document and more of like NLP based data, let's use sentence BERT as our preferred choice. Next is dense index. So for dense index, we're going to use CPU in a sharded fashion. Once we have the query embeddings, instead of searching on a GPU-based index, which is actually very expensive, which is fast but expensive, we're going to offload this whole piece onto a CPU. We can use sharded FAISS, Facebook AI similarity search, across multiple CPU instances. Sharding involves parallelism, so this is going to improve our memory efficiency basically, and this will allow us to scale without having the cost overhead that comes with GPUs. Next is merge BM25 plus dense. The reason for this is, for the dense search is not going to be enough. Just the dense search is not going to be enough. So we need to use, something like BM25 in conjunction with our dense search model. So it runs in parallel with the dense search, and they are both going to get merged to produce the search results, the final search results. Cost optimized hybrid pipelines. So yeah, basically what we're doing here is that we are optimizing the cost while maintaining our latency SLAs, right? So most of the GPU usage is sort of concentrated on embedding generation, and search and post-processing. Those sort of workflows are sort of offloaded to CPU infrastructure to minimize the cost of the whole system. So in the end, what we have in our system is GPUs where they matter the most, where they are needed the most, where inference latency is needed, where high parallelization is needed, and CPUs where they can scale the most. So where they can scale and where they can help us save cost as well. That's pretty much it for this presentation. I really hope you were able to learn something new from this presentation. And thank you so much for sticking till the end. Bye.